Today we're going to discuss modeling and prototypes as continued with our engineering design process. The unit big idea. I'm sure you all remember this by now. The engineering design process is a systematic, iterative, problem solving method which produces solutions to meet human wants and desires. The lesson big idea. At various intervals of the engineering design process, conceptual, physical, and mathematical models evaluate the design solution. Modeling. As we learned in the engagement, there are three different ways to represent our world. You have written and spoken words. You have mathematical, like formulas we use. We just used a formula for V equals IR for Ohm's law. Graphical, where you actually graph out what is happening. So, three different ways to represent our world. Now, modeling. During design process, you're going to check for proper design and note your areas of needed improvement. What needs to change? What can be done better? Conceptual, physical, and mathematical models evaluate the design process. So you're going to look at something conceptual, what you're thinking about, how would you design it, your physical design, and mathematical models such as a bridge. There are some cases that you cannot have a physical model because of the size of the project, and that's when you do a mathematical model. Usefulness of models can be tested by comparing predictions to observations in the real world. So you're going to make a prediction of what's going to happen. Conceptual models. They allow designs to quickly be checked and critiqued. Design may be refined and improved. Technical sketching is a design tool used to create conceptual models. So, we need some good drawers in here, right, guys? Technical sketching. For conceptual models, there are several types of technical sketching: isometric, oblique, perspective, orthographic. And we've already discussed orthographics. Isometric. Now you have 3D drawing of objects using true measurements. So you see the design we have here on the side? It's a bevel interior jambs. That's showing where you'd have putty. You have step Newton. Replicates your original steel beams. You've got your space bars. You've got your simulated projecting vent. Front and side are drawn at a 30-degree angle to the horizon. That is one of the characteristics of isometric. For more info, search for isometric drawing online. Oblique drawing. Now you see the difference with the oblique? 3D drawings with the width represented as a horizontal line, and you'll see the side view of the object is drawn at 45 degrees from the horizon. For more info, please search for oblique drawing on the internet. You could Google that. Perspective drawing. What you perceive. 3D drawings of objects where lines converge on one or more points. This is a beautiful, maybe an actual building. Beautiful design. It's one in Raleigh. I think it's a church that they're building. And they've been building that for the last 2 years. And you can see the intricate designs that's going into it. They're putting a brass dome on top. Perspective drawings are intended to be close to the human eye in observation. Can be 1, 2, or 3 points. For more information, look up perspective drawing on the internet. Physical models. Do you have mock ups or prototypes? A prototype is a working model to test a design concept through observation and adjustment. Please remember that a prototype is a working model. You want to see what's going to happen. You want to put it under different conditions. What happens when you get it under those conditions? A mock up simulates the look of an object and it is not functional. It will not function. It's just a pretty picture. Well, not a pretty picture, a pretty object sitting there. Mathematical models. Find a mathematical relationship that behaves the same way as objects that you are looking at under investigation now. So you may take a bridge that's been built and you will examine the way that bridge works and compare it to the way you want your new one to work. Mathematical modeling simulates how a system might behave. If you're building a bridge and you're looking at the way the water's going to flow in, how is the water going to wash against the bridge? How do you need to anchor that bridge for stability? You express your mathematical ideas precisely. You're looking at the circumference here. Circumference equals 2 pi r. 2 times pi 3.14 times the radius. You're using mathematical equations. Mathematical models. They create representations to organize, record, and communicate ideas. You use symbolic algebra formulas to represent and explain what the mathematical relationships are of your different parts. Computers have improved power and use of mathematical models by performing long, complicated, or repetitive calculations. Have you all seen the movie Hidden Figures? Has anyone seen that yet? That's a very interesting movie because it's showing John Glenn, I think is the astronaut, is showing how they were computing the trajectory of bringing him back into space, bringing him back to Earth from out of space. Example of a mathematical modeling. Example of mathematical modeling is the designer wants to create a hot air balloon designs without creating physical models. You can use algebraic formulas to represent whether you want to increase or decrease the lift of the balloon based on the inside volume or the temperature of the air. Calculations are communicated on spreadsheets or computer-based simulations. Has anyone ever written in a hot air balloon? Did you like it? I've never written in one. I don't know. I'm scared of heights, so. Huh? Oh, I think it's safer in an airplane that's enclosed. Good. Glad you overcame it. Creating a mathematical model. Now, in order to create your mathematical model, there are a few things you're going to need to do. You're going to determine the output you would like to achieve for the mathematical model. What is it going to do? What data information is available? What can you measure? What can you determine? You may be doing something that's going to use Earth's gravity, gravitational pull, frictional pull. Research for other mathematical models already created you can use. Now we're continuing. You need to identify relationships among variables. Your science concepts, such as Ohm's law, which we looked at. You want to create equations that relates variables, such as our Ohm's law, V equals IR. You want to check the accuracy of the model against a similar system or over time. We're going to look at properties of 2 and 3-dimensional objects. Because when you're drawing, some things you'll draw in 2D, other things you'll draw in 3D. Engineers and designers must understand basic principles, basic properties of both 2D and 3D objects. For 2D objects, you must be able to calculate area. For 3D objects, you must be able to calculate the volume and the surface area. So 2D objects, you're calculating the area, like the length times the width. 3D objects, you're going to calculate volume and surface area. You're going to need properties that will help you determine your modifications that are needed. That's going to be related to the function of the product and the marketability of the project. You want to make sure that your profit margin is met. If no one buys your project, then you're not going to have a good profit margin. Now, if you calculate area, area is the amount of surface of a 2D object. Some formulas that we have are here. For a rectangle, area equals length times width. For a triangle, area is equal to base times 1/2 the height. Circle, the area is equal pi times the radius squared. These are the normal formulas that you've been using in, have you all had, I don't think you've had calculus yet. What different maths have you all had so far? No comments, guys? I know you all have geometry. Is that still the 10th grade? Calculating volume. Volume is the amount of space a 3D object takes up. We have formulas listed below for some of those volumes. A rectangular box. V is equal to length times the width, but now we've added the height. So you've got length times the width times the height. The 2D for the rectangular box was area equals length times width. Now for the volume, is equal length times width times height. For a pyramid, the volume equals area of the base times 1/3 the perpendicular height. For a sphere, the volume equals the diameter cubed times 0.5236. A cylinder, the volume is equal to diameter squared times the length times 0.758. So you know that some of this is going to be calculations. We want to calculate the surface area. The surface area is the measure of how much exposed area a 3D object has. Formulas are listed below. For a rectangular box, the surface area is equal the height times the width times 2 times the height times the depth times 2 times the depth times the width times 2. Now for a pyramid, the surface area is equal to the perimeter of the base times 1/2 of the slant height plus the area of the base. A sphere, the surface area is equal to diameter squared times 3.1416. And lastly, for a cylinder, the surface area is equal to diameter times the length of a cube surface times 3.1416 plus the area of the bottom plus the area of the top of the part. Now, and ending this lesson, all models. It is very important that models function as close to the real world as possible. So when you're making your prototype, you want it to function as closely to your final product as possible. All models must be continually checked and refined during the design process. More than one of the 3 types is often used for the same product. And that concludes our lesson